So if I just had this problem where I was given this parametric function, x equals t squared minus 2t, and y equals radical t, and they said, find the area enclosed by this function and x equals negative 1/2. I really want a visual of this, okay? I really want to see what is it I'm doing, okay? Because without that, I may be able to make some progress, calculate some values, do some equations, but I really want to have a visual of what I'm doing. So this is where you can use, like I showed you, the parametric on your calculator, or get online. I'm sure there's all kinds of parametric graphers on websites. You could find it. But if we were to graph this, and here's what it looks like. So the blue curve is our parametric curve, and then x equals negative 1/2. And so first we have to identify what is it if they want the area enclosed by these two curves. Notice that I never said the x-axis or the y-axis. So that's a common thing that students fall into, is they see the graphs and then they form some kind of region using the x or y-axis. So for instance, they might look at this and say, oh, they mean this one. But it never said y-axis. It just said the area enclosed, the region enclosed by these two curves. It never said the y-axis, and this one would include the y-axis as a boundary. So instead, it should be, you see what it should be instead? This one here, right? Oh, but this poses a bit of a problem because our form is based on t, but it's set up, so this is set up in such a way that it's still based on, what did we say? Gt, f prime of t. Even though this is all in terms of t, it's still equivalent to, just f of x dx from x1 to x2. Now that's not going to work on this one. Why not? I don't think it will. Maybe it will. Yeah, it still will. It'll still work because it'll come up to here and it'll give us a certain area, and then it'll subtract that whole area. It'll still work. Okay, so what we need is we need first of all to know the direction of the curve. So which way is the curve going? Is it going this way, or is it going this way? So we can just try some points here. So this is increasing t. This is increasing t this way. So we need to find, this will be our t1 and this will be our t2. Okay, so how will we set this? So we need to find t1 and t2. How are we going to do that? Well, that's where x is equal to, where the x value of negative 1/2 is equal to the x values of the points on our curve. So it'd be t squared minus 2t equals negative 1/2. And so these will generate our t values here. So it'd be t squared, and so I'm going to multiply by 2 here just to get rid of the fraction. So 2t squared minus 4t is going to equal 1. Sorry, negative 1, so it'd be plus 1. Okay, so this is not going to factor. Okay, this is not going to factor, so what do we need? Yeah, or we could just use the quadratic formula. So you're either going to factor, if it does factor, and get your t values, or quadratic formula, which would be opposite of b plus or minus square root of b squared minus 4ac, which is 8, all over 2a is 4. Did I set it up right? Opposite of b, plus or minus b squared minus 4ac over 2a. I think it's right. So we got 4 plus or minus square root of 8 all over 4. Square root of 8 is 2 square root of 2. So we can factor out a 2 out of everything. And we get 2 plus or minus square root of 2 all over 2. So this t1 right here will be 2 minus radical 2 over 2. And this t2 will be 2 plus radical 2 over 2. And we're going to integrate from, so we're going to integrate from that t1 to that t2 of what? gt is radical t. And what's f prime? 2t minus 2. And that's an easy, we're just going to distribute the radical t's, multiply that out, and that's a pretty easy integral. And we're going to integrate from this t1 to this t2.
Did you start the recording?
Yeah, I did. Thank you. Yep. Okay, and so, I kind of talked through this yesterday, but the reason why this will work is because from here out to this far left point, we're going backwards in x. So from t1 out to this, call it t0, it's going to give the opposite of all this area under here. Because it's going backwards in x, and it's going to give you the area under the curve. And then as you go from t0 to t2, it's going to give you plus all the area underneath this curve. And so when you do all the area underneath this curve, plus the opposite of what's underneath this, you get exactly what's in the red. You see that? So it does it automatically. It will automatically, as you go from T1 to T2, give you that exact area right there. So I think the rest is doable. You're going to multiply this out, take the antiderivative, and then you're going to evaluate at your bounds here, and that will give you that area. Okay, how about if we want to know, figure out what t value is out here algebraically? What are we going to do to get that? So maybe call it the leftmost point, right? How do we get the leftmost point on the curve? He wants dx dt to be 0. Is that right? Yeah, because for a small, right there, for a small change in t, how much does x change? 0 vertically, right? So there's only vertical change right there. There's no horizontal change. So the leftmost point is where dx dt is going to be equal to 0, or 2t minus t equals 0, or t equals 1. How do we get the xy coordinates of the point then? Yeah, that's just the very nature of a parametric function. Given the t, it generates the different points. So then x equals 1 minus negative 1, and y equals 1. So I'm just plugging t into our original parametric equations. 1 squared minus 2 is negative 1. Radical 1 is 1. So this is at t equals 1, we get the point negative 1, 1. And so what's the equation of the tangent line there? What's the equation of that line that I've not drawn well? What is it? Oh, okay, but no, mx plus b isn't going to work because this is a special line, right? What kind of line is this? It's not an asymptote. It's a vertical tangent, right? A vertical tangent. So vertical tangents always have the form what? X equals something, right? Y equals mx plus b won't do it. Because it's not, it's y equals mx plus b is like the function form of a line. This is just x equals something. So x equals what? -1. Right? It's the x coordinate of that point. Okay, how can we test to see if this is asymptotic? So the question, there's some questions in the web work. Is there a horizontal, maybe as t gets very large, there's a horizontal asymptote. How could we check that? What limit? The limit as? T goes to infinity of what? We're seeing if there's a, it's going to level off, right? Of what? Of y. So, y is the square root of t, so as t gets very, very large. Do we have an asymptote or not? Square root of t. Is that asymptotic, or does that just increase indefinitely? Increases indefinitely, right? Square root of t just gets as big as you could want it to get. So there's no asymptote. But if this was leveling off, this is how we do it. We'd say, all right, let t get really, really large, and we want to know what y does to see if there's a horizontal asymptote. Okay, so I've tried to, in this example, tried to touch on lots of things in those last 4 problems. Hopefully that's helpful. And you got till midnight tonight to finish those. And you can use the email instructor button. Okay, there's a, at the bottom of every page with a problem, there's email instructor, so you can use it. Don't be, it's all right. I'll try to get back to you as soon as I can. Okay? So let's press onward here. Here's a parametric, here, this function, this blue function here. That blue function is a function you get if you rolled one small circle along a bigger circle. Do you see that? Do you see the small circle rolling on the bigger one? And so that curve, that blue curve, can be written with parametric equations. In fact, it's this right here. It's 5 cosine t minus cosine 5t, 5 sine t minus sine 5t is the curve that you would get if you rotated one circle, smaller circle, along a bigger circle. So that's an example of a parametric curve. Okay, that was free. You don't have to pay me for that. Okay, so I want to open... So we want to talk about polar coordinates. So polar coordinates is another way, it's an alternative to rectangular coordinates to graph things. Let's see what this is. All right, so here's an example, this blue one. That blue curve is an example of a curve that was generated with polar coordinates. Pretty slick. It's like butterfly, right? Okay, so we'll start with some easier ones first, though. But the idea is instead of x, how far right and left you go, and then how far up and down you go, polar comes from the word pole. So it's based on distance from the pole, or what we used to call the origin. Okay, so polar coordinates. Okay, so polar coordinates are based on distance from the pole, so this is called the pole here. And then we call that r. So the distance from the pole, or the distance from the origin, is r. So it's like radius, right? It's just like radius. Radius, distance from the center of the circle. So we use the symbol r to mean distance from the center of the coordinate plane, or the origin. Okay? As a function of the angle theta, and theta is our standard trig angle. So like that. So you see red? Yeah. So the red is showing, for instance, the angle, the standard angle swept counterclockwise from the positive x-axis. So given some angle that you swept, there's some corresponding distance from the pole, or r value, and then as theta changes, r changes, and it gives you points in the coordinate plane. So the way I've set this up here, instead of grid lines, what you have is called radial lines. So you have concentric circles and then radial lines, okay? Because concentric circles are constant values of r, right? So r equals 2. Well, how does r equals 2 graph? What is the graph of r equals 2? All points such that r equals 2. What would that be? Anybody? That's a circle with radius 2. Not sure why that's not showing up. Theta from 0. Anyway, so I don't know why it's not showing my software, but r equals 2 is the circle with radius 2. It's the circle right here. Okay. What about theta equals pi over 4? What would that, if you were to graph theta equals pi over 4, what would that look like? Would it be a curve, a line, a point, a circle? Yeah?
Be a straight line on this pi over 4 radial line?
Yeah. So would it be a line extending infinitely in two directions? Actually, no, it wouldn't. So I don't know why things aren't graphing here. It would, so theta equals pi over 4 is strictly in the first quadrant. So it would start at the pole, and then it would go like that. So if you're only, okay, so if you're considering r greater than 0, right? So if r is greater than 0, then this line right here would be the line theta equals pi over 4. If you allow r to be negative, so theta pi over 4 is like a direction from the pole. So if you allow r to be negative, r equals negative means you go backwards. So this would, you're right, this would be theta equals pi over 4. You can draw. But for r less than 0, for values less than 0. So oftentimes you'll specify that just r is greater than 0. And if that were the case, you would just get this part in the first quadrant. But if r can be less than 0, then yeah, it's the whole line. Okay, it's the whole line. So we plot points as, say, 3 r comma theta. So that would be 3 units away and an angle of pi over 4. So that's the point 3 comma pi over 4, r comma theta. And what would this point right here be? So is there 2 ways we could express that point? Let's express that point in 2 ways. That's one difference between rectangular coordinates and polar coordinates is in polar coordinates, there's more than one way to express the same point. So can you express that point in 2 ways? What's one way we could express this point right here? Okay, so radius is 1, yeah, distance of 1 from the pole, and you're seeing this angle all the way around like this, which is 5 pi over 4. How else could we express that? Negative 1 pi over 4. So both of those coordinates r theta express that point right there. Okay, so if we were to superimpose the rectangular plane on top of this, then what would the coordinates of this point be as rectangular coordinates? Right, so what coordinate am I showing like this right here? The length of that line? Is that y or x, the length of that line? He said y. Do you agree with that? The length of that line would be the y coordinate. Not sure? I hope you're sure. It's y. Y is vertical distance above the x-axis or below. Okay, so that'd be the y coordinate, and then your x coordinate would be like this. And so I've got this point 3 from the origin, a radius of 3, and the angle pi over 4. How would you get x and y? Okay, so you should be thinking cosine and sine are going to be the key to getting the x and y coordinates here. Right? Is it okay? You give me, yeah, okay. So the x coordinate will be, so this length right here is, this is 3, because that's our value of r, our distance from the pole. So the x coordinate would be 3 cosine pi over 4. And the y coordinate? 3 sine pi over 4. So this point in polar coordinates 3 pi over 4 is equivalent to 3 cosine pi over 4, 3 sine pi over 4 in rectangular coordinates. This is our x, and this is our y. Okay, so let's just generically pick a point here with coordinates r theta. What are the rectangular coordinates? Everyone should be able to write that down. So given any point in the polar plane r theta, what would be the corresponding rectangular coordinates that would give you that same point? Okay, and then likewise. Here's the point, say xy. How do I write that in polar coordinates? Okay, so don't cheat. See if you can figure it out. I mean, don't look in the book or online or something, but see if you can do the math. I'll hand out some stuff. And then work out by yourself, and then in a couple minutes maybe, see how you're doing, compare with each other. I have numbers now, right? So the y-coordinate's going to be this, and the x-coordinate's going to be this. And what's this distance right here? What is that? Okay, that's true, but we're given r and theta. So in terms of r and theta, actually we're going to use that for this one over here. What is this in terms of r and theta? That's just r, right? And then our theta is this. So x equals r cosine theta. And just like we did in the last example, now we're just doing generically for any point r comma theta. And then y-coordinate, r sine theta. So that's kind of the same as the one we did. But now if we're given x and y, here's x and y. Now we need to figure out what's r and what's theta. Okay? So what about r? So this is what you were saying before. X squared plus y squared? The square root of that, right? So the length of that hypotenuse is the square root of x squared plus y squared. Okay? And then what about the angle theta? So we know x and y, and we want to come up with theta. So how do y and x relate to theta, right? Okay, so theta, x, and y, we can bring those together through the tangent function, right? Tangent of theta is y over x, so then theta is tan inverse of over x. Okay, so these relationships are going to be important for transitioning between the two systems. X equals r cosine theta, y equals r sine theta, r equals the square root of x squared plus y squared, and theta is arctangent of y over x. So these are the relationships that connect these two coordinate systems together. Any questions so far? So let's just kind of maybe predict what some things would be. What would be All right, maybe let's just do some practice. I don't really get it. So no calculator. Say no calculator. So let's do these on sheet. So no calculator. This is for by hands. Understanding. Your work's good, as always. So these are given in polar, right? These are all r theta, and you're going to plot the point. You're going to do them all on the same axis. So just draw one axis, one set of axes, and then some faint circles. Do your best so you don't have to be perfect. And then you're going to plot these points, and then find the equivalent rectangular coordinates. You don't have to whisper. We can work together.
That might just that's made us. So do you remember what the names were? But yeah. Third. Yeah, we're gonna what the or the
Do you guys turn
yeah the unit with the same.
Okay, is there one of them you want me to do?
So the second piece. It's the same thing. Would you like that, man? Yeah. Oh yeah. Yeah.
Okay. Any questions? Is there one you want me to do? Are we good?
the last one?
The last one? The last one. So what does, first of all, what does the negative 3 mean? So negative 3 for R. So well, this will determine the direction that we go from the pole. But if it's negative R, then what direction do we go from the pole? Backwards from that direction, right? Does that make sense? So we want to find what this direction is from the pole, and then rather than going in that direction, we'll go directly opposite, 3 units. Blank stairs. Does it make sense? Yeah. So where's 3 pi over 4? Where's 3 pi over 4? What direction? What quadrant? Second quadrant. And let's see if I can. Isn't that it right there? Is it red? See the red? That's 3 pi over 4. So that's the direction of R. So if R were 1, we go out 1 from the pole. If R were 3, we go out 3 from the pole. If R is 4, we go out 4 from the pole. You get that. But we want to have negative, we're going to go negative 3. So where does that put us? Which quadrant? In the 4th quadrant, that's right. So we're going to, if this is the direction of 3 pi over 4, then this is how you go for negative R for 3 pi over 4. So it's going to go how far then? Here. This is negative 3. So even though they write R first in the ordered pair, you do theta first. You get the angle first, and then you go out for the pole. Because if you didn't, see, this makes no sense, right? Negative 3, it makes no sense until you have a direction. So go with the theta first. So does that make sense? That's negative 3, 3 pi over 4. Are we good on these? Can we go on?
For the second. So maybe
And then hopefully that first one you didn't need any formulas for when you wrote it in rectangular coordinates, right? You think about it. You don't just blindly go for a formula. You just look at it and you think about it and you go, oh, well, that's the point, right? So after you plot this point, no formula to get that x and y pair. Okay, ready to go on? So polar curves So I kind of mentioned that here. Polar coordinates are based on distance from the pole as a function of the angle theta. So therefore, polar curves have form r equals function of theta. Try that again. That's better. R is a function of theta, meaning based on the angle that you swept, some equation or formula will tell you how far you are from the pole at that point. So for example, R equals 2 sine theta. So this is telling us how to get R given the value of theta. You take the sine of the current angle, then multiply by 2, and that's how far from the pole you should be. So the way that we graph these is we start by graphing R and theta in rectangular coordinates with theta being the input and R being the output, and then we use this graph in rectangular coordinates to help us develop the graph in the polar plane. So we have to know our sine and cosine graphs really well and the transformations of those. So could you sketch 2 sine theta without? Some can. So can you do it? Can you sketch 2 sine theta in rectangular coordinates, right? It's going to be a wave curve, right? These wave curves. So maybe we think about, what's the max and the min of this function? We're going to have a min and a max. What's the min and the max? He wants 2 and negative 2. Agree with that? So you got to remember. So this is for those who never learned your sketching trig functions. This is going to be challenging. All right. And so then sine theta. Does it start at the max or the midline or the min? So what's the period of sine theta? How long in theta before it starts over? 2 pi. Okay. And then we know that it's broken up into 4, these sine and cosine graphs. We break them up into 4. We break the period up into 4 equal parts. And then, does sine theta start at the max, or the midline, or the min? So you should remember that starts at the midline. When theta is 0, sine of theta is 0. And it goes, what does it do? Goes up to the max, back down to the midline at pi, then down to the min, and then back to the midline. So we're going to take the information that we have from this to try to sketch the curve here. So here's what we do. When theta equals 0, in which direction do we go for theta equals 0? What direction is that point? Directly to the Right. When theta is 0, what is r? According to our graph here. 0. So what point is that? Well, that's the pole. Theta, whenever r is 0, you're at the pole, no matter what your angle is. So we're going to start at the pole. And then in the first, as theta goes from 0 to pi over 2, right, this is pi over 2, what does r do? So as theta goes from 0 to pi over 2, what does r do? Increases up to 2. Okay, so when we get to pi over 2, we're going to be here. But we have to think about that happening. I need to change this. We have to think about that happening as theta increases. Okay, so I'm showing black for positive r and red for negative r, okay? So theta is going to go from 0 to pi over 2, and as it does that, r is going to increase from 0 to 2. So here's a small angle. We might get a point with a small r, right? Like this. If we increase the angle a little bit, we're going to get a larger r, right? So as theta increases, we're getting farther and farther away from the pole. Larger r, right? Not quite 2 yet. So do you see what happens there? As theta increased from 0 to pi over 2, we got farther and farther away from the pole. Did you see it? Did you catch it? And so then when we go, I was doing good at the beginning and then it got a little rocky there at the end. Okay? And then, so now as theta goes from pi over 2 to pi, what happens to r? Decreases from 2 to 0. So you're watching the black there. As theta goes from pi over 2 to pi, the r is going to decrease back from 2 to 0. So take a little angle here. And now it's going to be a little less than 2. Increase the angle some more. No. And we're going to get even less, a little less than that. So see, r is decreasing as theta is increasing to pi. That's the best polar curve I've drawn all day. Okay? And then now what's going to happen as theta goes from pi to 3 pi over 2? As theta goes from pi to 3 pi over 2, what does r do? It's going to do what? Go from what to what? 0 to negative 2. So you'd be looking, where would you be looking on the graph there? So the black line is showing you the actual angle, so from pi to 3 pi over 2, but r is going from 0 to negative 2. Where is that?
First quadrant.
First quadrant. So the angle, the actual angle is the black, but we're going to be graphing on the red because these are negative r values. And actually it's just going to repeat what we already did in the first quadrant. You see that? Because r is going to go from 0 out to negative 2. Did you follow? All right, and then from 3 pi over 2 to pi, when the angle goes from 3 pi over 2 to 2 pi, r goes from what to what? -2 to 0, which will just overwrite what we already did in the second quadrant. Do you see it? Okay, so this looks like some kind of round shape. Circle, oval, ellipse, something. So let's have the calculator actually do it and see what we get. So what's our f of theta? I gotta save that. Can't lose that. That's cool. The butterfly. All right, so we're doing 2 sine theta. It's not it. Wow. Yeah, I thought I was doing something else, so we need to cut. I think I'm stuck here. There we go. I'm back. There, I'll save you there. Okay, so now I'm back, and we got, and we want to turn F on. Do it blue. That's a point. Black. And we'll sweep it out. Blue. Ready? Here it goes. And so now here's that third quadrant repeating, where r is negative, from -0 to -2, and then back in the fourth quadrant, repeating -2 to 0. Pretty cool. So this was what? R equals 2 sine theta. So you get the whole curve just from 0 to pi, and if you go from pi to 2 pi, it repeats it with the negative r values. What does it look like? Sure looks like a circle, doesn't it? Okay, so let's prove that it's a circle. How can we prove that it's a circle? We can use our relationships. Can we change this into x and y coordinates and show that it's the exact circle we're looking at? How can we do that? What are our relationships that get us x and y from r and theta? X equals r cosine theta, and y equals? So let's do the math and show that we get that circle. Well, I have 2 sine theta. It'd sure be nice if I had what? 2. No. I'm trying to change this into x and y. So rather than just sine theta, what would be nice to have? I'm trying to get this to be x and y. No, not theta. I'm trying to change this into x and y. So instead of sine theta,
Y.
no, r sine theta. If I had r sine theta, it would be y. Do you see? So if I do 2 r sine theta, what does that equal? I can't just multiply something by r, right? What does it equal? What does 2 r sine theta equal? R squared. Multiply both sides by r. And lo and behold, the right side is 2 y. And the left side is, what's r squared? X squared plus y squared. From our right triangle, right? R squared is x squared plus y squared. And so now can I change this into a circle? So x squared plus y squared minus 2y equals 0. I need to complete the square because the form of a circle, if we're thinking this is a circle, what's our equation of a circle? X minus h squared plus y minus k squared equals r squared, meaning the radius. So I need to complete the square. What completes the square? Half of this squared, right? So you take half of -2 and you square it. So I'm going to add 1, but if I add 1 here, I got to add 1 here. And so what do I got? I got x squared plus, we got a perfect square now, equals 1. Y, what? Minus 1 squared. Pre-calculus. Got to remember it. What's the center of the circle?
0, 1.
0, 1. X minus 0 and y minus 1 gives 0, 1. What's the radius? Is that the circle we have? Center, 0, 1. Radius, 1. Got it. So this right here, r equals 2 sine theta, is the same as this circle. The circle with center 0, 1, radius 1. Any questions? All right, so how about, could we write y equals 1 plus 3x? What is that? What does that graph has? Line, right? Okay, so could we write this as r is a function of theta? Meaning r equals an expression with thetas in it. So this is going the other way. So you gotta know the relationships between rectangular and polar coordinates and know some and be good at algebra. Do it. Hopefully we had success with this. So we can start by rewriting this as what? R sine theta equals 1 plus 3 r cosine theta. And then we have to solve for r. We got to solve for r as a function of theta. Okay, and what do we do next? We're trying to isolate r, right? We're trying to get r equals something. So how can I do that? How can I get r equals something? What, Kevin? Factor r out, right? We're left with sine theta minus equals 1. Last step, r equals? So we get this crazy fraction, right? 1 over sine theta minus 3 cosine theta. Just to graph a line, right? Why is it so crazy? Why is that expression kind of complicated just to graph a line? Let's do it. Why is it such a kind of hairy equation? 1 divided by sine theta minus 3 cosine theta. So here's how it gets graphed as theta increases from 0 to 2 pi. So it's just 1 plus 3x. What's the big deal? Why is this just kind of a weird kind of a fraction equation? Why? Yeah?
Just because as your angle is changing, it's the distance from the center is constantly changing.
Okay. So the distance from the center is changing. Well, that was true about the other one we had too. It's really about compatibility, right? This coordinate system is about what? Distance from the pole and angle. So when you take a line and just cut it through here like this, it doesn't really relate to this way of plotting points, right? So a line like this that doesn't go through the pole, it kind of just cuts through like this, it doesn't really relate to r and theta directly. So when you find the polar function, it's going to be something more complicated and weird, because this is kind of like an alien in a foreign land, right? This doesn't really belong here. It's not based on circles, distance from the center. And it's not based on the angle from the x-axis. Okay. So let's try some more of these polar graphs. So these are kind of cool. Let's try 1 minus cosine theta. Here we go. So we're going to try, turn this one off. So we're going to try 1 equals cosine theta, 1 minus cosine theta. Okay, what are we going to get here? What are we going to get? So we need to graph like we did before. We're going to graph the r is a function of theta in rectangular coordinates first. So can you sketch that by hand? Do you know your trig functions from pre-calc? Can you sketch that 1 minus cosine theta? So we can start by asking what's going to be the maximum and minimum values of that. What's going to be the maximum and minimum values of 1 minus cosine theta? Anybody?
0 and 2.
He wants 0 and 2. What are the max and min values of just cosine? Or opposite of cosine, doesn't matter.
Negative 1
Negative 1
and 1.
to 1, now we're going to add 1 to the whole thing. We're going to move it up. So it's going to go from 0 to 2, right? So we'll do that in blue. So 0 to 2. Okay? What's the period of this going to be? So how long is this going to, how much theta do you need for this to start repeating? It's just cosine theta, so 2 pi. Okay, where's the midline going to be? Where's our midline? 1. Okay, and then we're always going to break up our period into 4 equal parts. So it's going to be pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so where's this 1 minus cosine theta? Where is this going to start? The max, the midline, or the min? Is it going to start at 2, 1, or 0?
1.
0.
I heard all 3. So we better know. So cosine, just cosine by itself. Max, midline, or min? Just cosine. Max. Which would be 1, just for cosine. Now we're going to take 1 minus 1. So it's going to start us at the min. It starts at 0. And then from there, we're going to the midline, up to the max, back down to the midline, and the min. Okay, so without your calculator, so based on this graph, can you make a sketch? Can you sketch by yourself what the polar graph will look like? So you're going to take it a section at a time, and you're going to ask, as theta changes from this to this, or as we rotate, say, from this to this, what will R do simultaneously? And then you go to the next part. As theta goes from, say, pi/2 to pi, what does R do, etc. And then see if you can make a graph of this thing by doing that. So everyone, try, see if you can do it. If I just do a bunch of examples, you're going to go home and you'll have no clue. So you got to try it yourself. So we're going to try to sketch the polar graph based on our sketch of R and theta. This. It is right. That's right. Yeah. People are getting it.
That's all kind of same idea.
Not quite, because you don't have anything in your first quadrant. So if you got your first quadrant from 0 to pi/2. Right. Okay, so from 0 to pi/2, you're thinking about that angle increasing from 0 to pi/2. According to the graph we made, what does R do? So according to our graph, R increases from 0 to 1 as theta increases from 0 to pi/2, 0 to 1, right? Do you see that? So what will that look like? So as that angle increases from 0 to pi/2, we're going to start at 0 and we're going to end at 1. And all along the way, R is going to increase more and more. So like there, there, there. So do you see as for each angle line that I go there, I'm further out away until when I get to pi over 2, it's 1. Kind of like the last one. But then what? What about from pi over 2 to pi? It keeps increasing. R keeps increasing up to 2. So it keeps increasing. So with each radial line, I'm getting R is increasing out to 2 when we get to pi. And then from pi to 3 pi over 2, decreases down to what? 1. And then from 3 pi over 2 to 2 pi, decreases to 0. So with each angle that you come in like this, R is decreasing along those radial lines. Do you see that? So let's have the computer do it. 1 minus cosine theta. Here it goes, watch. I gotta turn off this. So we're graphing it in blue. So the right idea, but wrong points. Trust me, if you do what I did, that's 100%, okay? So you see what happens. So it went out to 1 in the first quadrant, then out to 2 when theta got to pi, and then back to 1 from pi to 3 pi over 2, and then back to 0. So this is called, what does it look like? Kind of looks like a heart, right? So it's called a cardioid. Not cardioid arrest, just cardioid. Okay, let's try something different. Let's try another one. So let's erase so we can see it in its true form there. So there's the cardioid. Okay, so let's try. Let's try 2 sine. Let's do 3. Crazy. 3 sine 4 theta. Okay, before we do that, I want to do something else. Sorry. Let's go back to that cardioid. 1 minus cosine. That was a good example to do something else. Sorry. So we'll do this one next. But for this, can we find the top? What's the coordinates of the top of the cardioid? So what are the coordinates of the top of the cardioid? How would we do that? We're going to use a principle that we had in the last section. It's not a limit.
Tangent line?
Okay, so we think about, so what's true about the tangent line at that point? Horizontal, right? So at the top, we're going to have a horizontal tangent. It's supposed to be horizontal, okay? And so what's true about a horizontal tangent? Mathematically. How are we going to pinpoint that mathematically? What's that? Yeah, but how are we going to find that y coordinate? What equals 0? Right, so dy dx equals 0. So, but we have r as a function of theta. How are we going to get dy dx? This one actually does not lend itself very well to doing that, because we could do that same techniques before. We get r squared equals, we get r minus r cosine theta. Well, then we have x squared plus y squared equals, what's that? Square root of x squared plus y squared minus x. This is kind of, that's okay, it works, that's true. But yuck, right? So this doesn't really lend itself to anything we know. Like the last one was nice, we got into circle formula. So yes, that's true, and we could do what, implicit differentiation from Calc 1. We could differentiate term by term, but no fun. So let's do something else. When we have, so dy dx, we can consider, we know that y is a function of theta, right? Y equals r theta, r sine theta, right? Where r is this function of theta. And we know that x is r cosine theta, but r is also a function of theta. So if we found dy d theta and dx d theta, how could we get dy dx from those? No. If we had dy d theta and dx d theta, yeah. If we took this derivative dy d theta divided by this one, it would be dy dx. So how do we do dy d theta? How are we going to do dy d theta? R is a function of theta times sine theta. How are you going to take that derivative? Product rule, right? It's two functions of theta. So we're going to have r prime, or dr d theta, times sine theta, plus r times cosine, product rule. And then dx d theta will be dr d theta times cosine theta minus r sine theta, right? Because the derivative of cosine is negative sine. So then dy dx is what? Ratio. So this ratio right here and we need now to get our highest point on the cardioid, which is where that tangent is 0, we need this whole thing to equal 0. And what makes that whole fraction equal to 0? What makes a fraction equal to 0? Numerator. So if, in this case, all we really need is the numerator. We need that numerator to be 0, and we want to get theta and r that does that. Okay? So let's find dy dx. dy dx is going to be, in our case, dr d theta, which is, it's dr d theta, sine theta, right? It's the derivative of r with respect to theta. So here, so if r equals 1 minus cosine theta, then dy dx is going to be sine theta times sine theta plus r is what? 1 minus cosine theta times cosine theta all over sine theta again times cosine theta minus 1 minus cosine theta sine theta. And then we see where the chips fall here. So we got sine squared plus cosine theta. Okay, so what we want to do to solve this as a quadratic, we want to get it all in terms of cosine. So we're going to change the sine squared to 1 minus cosine squared. So the sine squared, we're going to change that using the Pythagorean identity to 1 minus cosine squared theta. And we're going to have plus cosine theta minus another cosine squared theta, and that equals 0. Okay, so we're going to have a quadratic and cosine. So we have, and I'm going to change the sign too. So 2 cosine squared theta minus cosine theta minus 1 equals 0. Does it factor? I think it does. Minus 1 plus 1. There we got it. Okay, did I lose you? So we wanted to know where this horizontal tangent is. That's where dy dx equals 0. So dy dx is this big ratio here, so we need the numerator to be 0. So we got the numerator to 0 makes the fraction 0. Okay? So now we want to solve this for 0. That means we want to get it all in terms of cosine or sine. Well, since I have cosine to the first, I want to get it all in terms of cosine. So sine squared is 1 minus cosine squared plus cosine minus cosine squared. And then when I get that into quadratic form, I have this, and then that factors. And so which angle is going to give us that second quadrant angle? Is it going to be this first term or the second factor? So that first one there is going to give us our second quadrant angle because it's going to give us 2 cosine theta plus 1 equals 0, or cosine theta equals negative a half. Who knows their unit circle? Who remembers their unit circle? Cosine. Yep, 2 pi over 3. That's 2 pi over 3. Okay, so then theta is going to be 2 pi over 3. How do we get r?
1 minus cosine theta.
Yeah, 1 minus cosine theta, and we know that cosine theta is negative a half. So 1 minus negative a half is 3 halves. So r is going to be 3 halves, 2 pi over 3. And that's right where that is. Look, it's halfway out between 1. Here's 1. R equals 1 and R equals 2. We're at halfway out, 3 halves. At an angle of 2 pi over 3. How would you find the x and y coordinates at that point? X and y coordinates at that point. Yeah, r, so you got this. You got r theta. You use your r cosine theta, r sine theta. So this we did right here is generic though for all problems, right? So I just did this first dy dx is based on your y equals r sine theta, x equals r cosine theta, and then here's where it was for our example. But this is your dy dx, okay? Okay, so we're on track.